Hello everyone, this is week 8. Today we will be talking about simulation using zero-order halt methods, and we will see some applications to optimization using this zero-order halt method. Now, essentially what we're going to do is we are going to pick a transfer function here, and we know that we can calculate or simulate these dynamic systems using differential equations, and we can use some differential equation solvers as we have looked at it in the last video here. But today we will be trying to solve it using basic mathematical operations using the zero-order halt methods. Um, Well, in order to do that, what I'm going to do essentially at the end of the day is I'm going to abstract it away from MATLAB so that you can go ahead and use C, code it in C, and use maybe some GPU in order to run simultaneous simulations at once and then try to come up with an optimal solution or well, solve it in C, basically. So this code that we are going to develop today will be portable to C, and I think, in my opinion, it's quite nice to have this ability here. Because throughout this course, we have always focused on MATLAB, but MATLAB is just convenient to use, but we don't really have to use it when we know the theoretical basis of it. So let's dive into it. First, the problem is to convert this transfer function into a more usable representation. And for that, we will use basically differential equations, but we're not really using high-order differential equations for simulations. It makes more sense to use low-order differential equations. For example, we have a third-order system here, but ideally what I want to have is three first-order differential equations, because this would be a third-order differential equation. If you have three first-order differential equations, which we call state space in control theory, um, then it's quite easy to use the zero-order halt method there, because we can numerically approximate the derivative or the integral. Since we will have only first-order differential equations, we know that we need only a derivative or an integrator for it. So that will ease the process here. So let's start with the first one. Before we get to it, what we need to know is we need to convert this transfer function into a state space representation. So for that, we can use some canonical forms. We have controllable canonical form. We have some modal forms. We have also, we can also use TF to SS in order to convert it. Let me show you. Help TF to SS. You can also use MATLAB, but I want to abstract it away, so you can feel free to use TF to SS. But what I'm going to do is I'm just going to manually code it here. As you can see, it will convert this transfer function into this state space representation where we have three variables. Two of them are pretty familiar, the input and the output. An extra variable is going to be the x, which is called the states. And we will use these states in order to solve the differential equation behind the scenes, but then this relation will basically convert it into our transfer function. This is not a unique representation. You can have infinite amount of them, so you can just pick one that suits you the most. Most of the time, since we're interested in control, most of the time we're going to use the controllable canonical form. There's also an observable canonical form, but let me show you what the controllable canonical form is. All I do is I'm just going to Google and find the first one here. Here you can see there's this notation where we have the coefficients of the denominator and the coefficients of the numerator, which we can easily get. And then it goes like this. It defines a dummy variable, x1, and we assume that the derivative of x1 is x2. Each time we take a new derivative, we just assign it a new variable. This way, they will depend on each other, but then the next variable will be used for higher order terms. Therefore, we will end up in a matrix here, but each of them will represent, each row of them of this equation here represents a differential equation, a first order differential equation, but we have n of them, so it means that we have the nth order differential equation. We can just substitute it back in order to end up in the high order differential equation that is represented by the system. But here we will use this representation here. So you can see it starts with 0, 1 because the next one is going to be always the new variable, or on the right half, on the right hand side here. Well, here we can see x1 dot will be x2, x2 dot will be x3, it goes on like that. But the last row is basically the denominator coefficients in reverse. The highest order term is bn minus 1 here, as you can see here. And it is normalized here, so we don't have s to the power of n. So you can just use this controllable canonical form in order to convert this into state space. And that's exactly what we are going to do. So I have opened up a script here. Now, first I'm going to acquire the numerator like this. So let me check if it's correct. And the denominator. So that's better. Let's check what num and dan are. There we go. We have 1, 11, 34, 24, and also 1. So the next step is to create kind of this matrix here, A, B, and C. We don't have D because, well, we are not quite checking everything here. What we can do is we can check if the numerator first term here is assigned. If that's the case, we have a biproper transfer function. That means that we will have a constant term D in our representation. So y is equal to cx plus du here. And if it's not a biproper, if it's a proper transfer function, d is always going to be 0 because this is the direct connection between input and output, and you have to be able to partially fraction this transfer function if you are going to end up with d. If it's a proper one, you don't really need to bother with that because d is 0. So you can put an if statement here if num1 is basically, if num1 here is not 0, so if this is not 0, then you can see it's basically biproper, so you have to assign stuff, else you can just skip and say, okay, d is equal to 0. There we go. Well, I'm not going to bother with this first part because I'm not developing a universal kind of example. I have a specific example, so I don't want to make it more complicated. So we know that d is going to be 0. We have the numerator and denominator, and we need to assign these coefficients here so that we get basically the formula here, so that we can use the formula here. So yeah, let's basically do the following. Now, first of all, even though we have dan equals 1, what we can do is we can assign dan into, divide dan to the first term here, so that we can assure that we fit this kind of structure here, where you can see that the highest order denominator coefficient here is going to be 1. So I'm going to throw this in so that we are assuring ourselves. So then I'm just going to directly use these coefficients here to assign stuff. For example, A0 is going to be denominator 4. This is A0 here, A1, A2, and then we're basically almost there. So A1, 3, 2 is going to be A2. Since we have normalized this stuff, we don't need to use dan1 here. And similarly, we are going to use B2, B1, and 0 here. So B0, B1, B2. This is going to be B2 is the numerator here. This is also the numerator here. So let me maybe change their order. Yeah, seems like it. So once we have that, I'm just going to use the same PDF here. I'm just going to plug it in. So A is going to be 0, 1, 0, and then the next row will be 0, 0, 1, and then the last row will be minus A0. You can look it up from the PDF, minus A1, minus A2 here. B is always the same if you use the controllable canonical form, only the last row will be 1 and everything else is going to be 0. And then we have the C matrix, which is going to be B0, B1, and B2. Of course, it is possible to generalize this so that you check the order, then check for the by properness, and then just end up in this here, because you can see it's always, you can just basically use the denominator. I guess flip was a function here. Flip denominator. You can flip the denominator and then put a minus sign here so that you get basically these terms here. And you can just then assign it to temp, for example, and use temp from the starting point up to n minus 1. So you get these coefficients here. Then you can use this instead of this here. Of course, you have to also embed a 0 vector here and a identity matrix here. So it would kind of look like the following. You would have zeros, and then I guess 2 by 1, and an identity vector here by 2, I guess. And then you would have a 0 here, and then this term here if you have that. So I'm just going to plug it in, but you get the idea. Here will be something flip, but I'm just going to assign it like this here. So you can see this should be basically it. So let's see if it works. We have an issue here. Oh, because we don't have this 0 here. So it makes sense. So you can see this is basically the same. So you don't really have to create this here, because you can then use the numerator here. If you need to revert it, you can use flip, etc., etc. So here what we also need to do is we need to get the length minus 1 of the denominator in order to get the order of the system, and then plug in n, and then just do all the math that's necessary. So it's not that difficult to come up with a general solution here, but I'm just going to simplify it for you for the moment, because we are not really interested in the details here. And since when you are going to stay in MATLAB, you can just use TF to SS. I'm just showing you the portable version here, basically. So now, up to this point, we have basically the system here. And if you are not sure if you did it correct or not, what you can do, you can just go ahead and open up TF and then SS, and then use A, B, C, and D, and check if this checks out. So let's see. So that was the result. This is the transfer function. It seems like we're good to go. So this is basically the same. So we did not mess up anything. So now, what are we going to do? Well, the task here is to compute the step response of GS based on the zero order halt method. So we're going to compute a step response here. Now for that, what we can do, of course, again, is to pick a settling time of GS, step info, for example, GS here, and see what the settling time is. In our case, I'm going to stick with 5, and again, I'm just trying to simplify the example here. But what you can do is you can just check the step info here. Of course, if you're in C, you are not going to be able to do that. But then what we would do is we would look at the poles here, because we can solve the poles of this transfer function here. Of course, then the order is going to be a limiting factor here, but let's assume that you are going to code it up to 4 or 5 so that you can solve it. Or if you don't even have that capability, what you need to do is basically you need to use a while loop and then check if we are reaching the settling time whilst we are doing all this old calculation stuff here down in a moment. So basically you then are not going to define a settling time. You will just pick a, for example, 1 millisecond sampling time and try to solve it on the fly. Now, let's continue. I'm going to choose a 0.01 sampling time here and a 5 seconds of final time here. Now, at this moment, I can assure you that you should actually look for better solvers here. What I mean by that is the following: zero order halt method is not the optimal one. You had basically a homework where you experimented with this, I guess homework 1. So you can look for Runge-Kutta, you can look for Hoyne method, etc. But as you might know, Hoyne method is not quite the way to go. The Runge-Kutta, fourth order Runge-Kutta would be the best. And I'll explain you why you might need that. But let's go. Let's just directly continue here with our zero order halt method. So far we have converted the transfer function into a 3x3 matrix representation. So it means that we will solve 3 differential equations of first order. Now, we have defined a time vector. Just for the sake of simplicity, I also calculated the sampling time here. So what I need to do is, and what the zero order halt method is in a nutshell, is that we have an equation that looks like this, a times x, and then we have y equals c times x plus du here, where we don't even have d because it's 0, but it's generalizable here. So, well, you know the geometric interpretation of the derivative, which roughly states the following, that this can be approximated by the limit of x plus, let's say k plus tau minus x k, let's call it k plus 1 times tau, k times tau, the whole thing divided by tau basically, or tk plus 1 times tau minus t k times tau. Here this is, of course this is in parentheses, but I'm going to erase it anyway. You can see that k plus 1 times tau and k times tau, this is exactly the thing that I've written down here. So we take the time vector or the x-axis, we look at basically delta x divided by delta t. And delta t is basically 2 instants, you pick 2 time instants, or in this case x-axis instances, and take the difference. So here we take the difference, and taking this difference in time represents tau, so I'm just going to erase this whole thing and call it tau. That's basically it. And by the way, here the limit tau goes to 0. Tau goes to 0. There we go. So this limit is the geometric interpretation of the derivative, which is basically the slope of the curve that we are interested in. So instead of doing that, picking a small tau and looking for this ratio here, we can end up in the derivative. So that's the basic idea. And well, this term here is going to be basically used instead of the derivative. And instead of calling this k plus 1 times tau times k, what we can do, we can also pick k and then k minus 1 times tau. So that can be done. And since we're already on a computer and we are using a programming language, this basically represents the discrete time instances, and we are going to use the array indices instead of these because it will directly correspond to them. So instead of multiplying that with tau, because this is kind of the continuous time way of defining stuff, we can drop this tau and say that k and k minus 1 divided by tau is basically the approximate derivative if tau is small enough. Now this tau is small enough condition here is quite the thing that will downgrade our performance here, because the bigger the value here is, the less in or the more inaccurate the results are going to be. But yeah, we'll see. Now this will be equal to a times x, but of course again k times or k minus 1 times tau, so I can drop that, plus b times u k, and c times xk. Of course, everything will be k minus 1 because I'm using k for the newest value and k minus 1 for the previous one. So I'm going to use previous ones here. And we don't have d, but if you have d, you can just plug it in here. So now from the differential equation, I ended up in the difference equation. And I can still manipulate this. I need to multiply everything on the right hand side with tau. So tau times a and tau times b. But I can then get rid of this parentheses here. And I can also see that I have xk minus 1 here on the left hand side. And I have also xk minus 1 here on the right hand side. So I'm going to just add 1 to it here. Since we are on a matrix, I can just add an identity matrix here. Since the size is 3, that's going to be it. There we go. So this is basically zero overhold method. And here we have basically the difference equations here. Using a for loop and these difference equations, I can just directly go ahead and use any programming language and arrays in order to simulate the whole system or the dynamic behavior. And it all relies on the fact that tau is small enough. So we'll talk about that, and the way of improving this is using differential equation solution methods. Maybe wrong a kutta, but we'll stick with this one. So, yeah, I'm going to define these as discrete A, B, C, and D variables here. Since they kind of correspond to that, x is equal to a times x previous plus b times u, and then y is equal to c times something. So I'm going to stick with a notation. That means that we can come up with matrices, discrete matrices here, that seem to do the same. So AD for discrete, I don't need this parenthesis here. And then B discrete is going to be this one here. Of course, C discrete is equal to C, but let's stick with that. And this is the difference equation that I'm going to be interested in. There we go. Now, let me move this to the top. Now, of course, this doesn't exist, so let me get rid of that. There we go. Now, if you still want to check if you are on the right way, what you can do is you can just define the state space model here, and then provide AD, BD, CD, and 0, and then tau as the sampling time. So this should give us basically, yeah, we didn't run this. So let's run this. There we go. Now we have the sampling time here. I'm not sure if we are able to convert it into a transfer function anymore. Yeah, it uses some discrete time transfer function to represent that, so it's not quite easy to check this out. What you can do is you can just apply step to both GS and this result in order to see if it's representing it right or not. So you can maybe check that out, but at the time being, I'm going to skip that. So now, what we need to do now is the following. We need to use a for loop here. So it's going to be something for, and because what we are going to do is we are going to use the time instant k, and we're going to look at the previous time instance or the previous values of these variables x and u, and we will calculate the new estimates. So it's kind of an iteration. And what we need to do is, or what we like to do is, we would like to store the whole process here. So we need each variable for each time instant to have a certain variable. So we need to define a memory. And for this memory, we're looking at the time vector. And we need to remember the fact that the ABCD matrices are basically matrices. So if I calculate or multiply something with A, you will need a vector. So let me define A, for example. I need to let me run this again. So we have A. So A times X is not actually a scalar operation. It's going to be a vector operation. For example, this. So I need a column vector for the time instant, and the result is going to be a time vector also because it's still x. So by checking this multiplication, I can see that x for k should be a 3 by 1 vector. And I know that I have this as the time vector, and for each value I'm going to store another vector. It means that the amount of elements in this vector times 3 is going to be the structure that I'm going to use to store x. And that translates into 3 comma length t. So I need to have a 2D vector here. And the idea is to basically define this and then use, for example, the first time instant. We messed up. So all rows, the first column, or the first two columns, for example, this will be, for example, k minus 1, this will be k. I will look at the previous values here, and the k instance is going to be this row here, and I have multiple of them. I have many of them here. So the for loop will start here, for example, from the second column here. It will calculate the values based on the first column here, and then it will go to the next column, look at the previous column, go to the next column, look at the previous column, and so on and so forth, until we reach the whole or the end of this matrix here, or the time. So we also are going to need some additional variables. So 1 by length t basically here, because it's just going to be a scalar for each time instance, and y for the output. So this is input output, and this is what we are interested in. But x is here a more complex structure because we have three differential equations. X1, X2, and X3 are the variables of them, and I'm keeping track of each signal because their combination is going to be representing my output here. So yeah, of course we are interested in the step response. That means that this should be a special vector, and we're okay with just providing ones here. We don't really have to simulate the uprising of the step here. If you want that, you might also look for that, but we are okay with applying 1 from t0. So yeah, at this point we're almost ready and we're almost done. what we need to do is we need to code this for loop here. So we will start at 2, and the reason being the following. We need to use k minus 1 here in our equations. By the way, let me just take the equations away here and just uncomment them, indent them, put some semicolons. Now, it will start with 2 because I will subtract 1 from it. So the indices in MATLAB start with 1. So k minus 1 should be at least 1. And if I provide 1, it will become 0 and I will get an error. Now, up to length t, because the whole time vector, the whole spectrum is needed here. Now, ideally I should be able to do the simulation, but here we have a situation where we're not picking xk, which is possible in MATLAB. You can define a 2D matrix, but then access it like a 1D object instead of doing it like this. So don't confuse that here. So what we need to do is we need to access the kth column. So it means that all rows and kth column should be equal to all rows k minus 1th column. Now, since u is a scalar, y is a scalar, I don't really have to provide the row information here. But here, since I have, again, x, all rows, the k minus 1th column here. So that's going to be basically it here. So once we've done that, let us create a figure here. And there we go. Now let's call the x label time and seconds. Y label is not that important. Let's give it a title. Step response. And let's plot t comma y. As you can see, we have t and y here. Let me just give it a color maybe, and then align with. There we go. So clear, CLC, run one. There we go, we've created a figure, and it is quite interesting. Now we can check if it's correct or not in a moment, but what we see is we have this this interesting behavior where we drop down to 0 for the last elements. And the reason is actually interesting, because if you look at the for loop for length t for the last index, you can see x is pretty much assigned here. So this equation, which is by the way the dynamic equation, is not causing this issue. But then you have the static equation, which is basically one sample behind and uses the old information, but yk, which would be the last element here, so y length t is never assigned here. And since we're looking at y and the last value is 0 because we've defined a 0 vector here, we can see that this never is updated here. So what we want to do is we can just go ahead and take this and plug in length and then t, and then yeah, that's pretty much actually length t here. So yeah, I don't really, well, if you're going to stay portable, we need to leave it like this, but I'd like to just maybe use and instead of this, or sometimes in C, K also works here. I am interested if it's also going to work here. So it shouldn't actually, but we'll see. In C, sometimes you can use that for accessing the last element here, and it seems like this is also the case here. So we fixed that by just calculating the last sample here, and we're basically good to go here. So what we can do is we can use step So I'm just going to use a new figure. I'm not going to bother with plotting on top of each other. Just use step, GS, and visually compare them because we have lots to cover here. Take some time. And there we go. So it seems like the values, the shape is similar. Yeah, so that's basically it here. We can decrease the quality, and sometimes it can also cause even instability here because we have tau here. So let me just increase it. And let me show the amount of points that I'm using here. So 501. So 500 cycles are used to calculate the step response at the time being. And if I drop it down to 51, let's see what's going to happen. It might even cause some instability, or it would look ugly. Let's see which one it is. Let me run it again to be sure. Well, it is still quite working, I'd say. The exact comparison could be possible to if we just do it on top of each other. It seems like I need to do this. So y comma t and then s and s. And let's have red. Let's have black. So let's run back. We don't use figure 2 anymore. We need a semicolon here. And I guess I'm going to use just same final time. There we go. You can see it's a bit off here and here, but that's not going to be the case if I increase the samples, the amount of samples that I use. You can see it directly matches now. What happens if I pick even a worse value? This should mess up probably the whole response here. There we go, instability. So of course there's a limit to it, maybe 0.3. Yeah, you can see 0.3 is very ugly and it's not really working. You might ask yourself why you would have to pick or why you would like to pick a sampling time or less samples, basically. Here, the length of t it corresponds kind of to the amount of cycles and also therefore to the computation time here. The lower or the less amount of samples you use, the faster you will calculate the response. And at the end of the day, we will look at optimization. And for optimization, each possible simulation or objective value calculation should take the smallest possible amount of time in order to be able to see the optimization, the end result. If it takes too long, then the optimization will also slow down because you might need to try thousands of different values and each needs a calculation or computation time. So therefore we would like to drop this down or drop the amount of samples down as much as possible. And it seems like 0.1 for the time being is a good approximation here that we can use. Of course, this could be an approximation. There's a trade-off here. And if you're okay with the approximation, even though we have slight differences here, I might be okay with this. I might not push it to 0.01 to have the perfect value here, because most of the time we look for ISA values, ITSA values, so integral time errors, square errors, absolute errors, or whatever, to optimize stuff. So therefore, sometimes this much difference is not really bothering us. For quick results, we might opt for this tau value here. Let's stay at this tau value here. So as you can see, we have also validated that our simulation works basically, at least visually, based on one sample here. So we have used the zero order hold method, and the zero order hold method consists of the geometric interpretation of the derivative or this limit on its own. It's based on its limit here. And if tau is small enough, this should be basically the difference in the x vector divided by the difference in the time vector, which is the sampling time, should give us the derivative. If you put it here, you get the difference equations that are shown here, and then you can use this to simulate it. That's for the first part here. So write a code that computes the derivative of a given vector. Let's look at this example. This is a quick and small example here. So let's call it f derivative. Let's just code a function that does this job here. Derivative dot m here. So function, the output is going to be dy, and the function name is basically f derivative, and we're using basically y and t, of course. So, by the way, let me show you something here. My editor here created some stuff. Let me show you why it can be useful. So most of the time we focus on the coding of functions, but if you call help on f derivative, you can see that basically it uses this structure here in order to highlight stuff. In my terminal, we're not quite able to see it, but in the MATLAB terminal, this might also look visually more appealing. If you look for the documentation of the f derivative, for example, which doesn't exist and which we've created here, that MATLAB is going to load up it in a minute. Come on, there we go. You can see the name is that. Then we have the description here. So you can use it like any other MATLAB function for printing out the documentation, the syntax, etc. So most of the time we don't use it, but since it generated, let me show it to you. Now, what are we going to do in this derivative here? Well, this is basically the numerical derivative, which means that we will use the difference, and we are going to basically use the same limit that we did here. So let me just copy this. But here we are talking about a vector, so it's going to be scalar. So we've called it y, so let me just call it y. And that's basically it. Now here, we don't know what tau is. But since we have the time vector here, tau is going to be t2 minus t1, because you can use any other consecutive values out of the vector t, but yeah, it is a linearly spaced vector. I assume that because it's time. So yeah, so we've calculated tau. Now what we need to do is we need to just calculate, because we can drop this stuff here. There we go, divided by tau. So this is going to be dy and then k here, or k plus 1, depends. Let's call it k and then k minus 1 and k minus 1. Doesn't really matter at this point. So this is basically the operation that we should do. And you can again do it with a for loop where k is equal to 1 up to length t and end. There we go. Of course, what we need to do is we need to generate also dy here. Dy equals zeros and then size of y. So the same size. And the k minus 1th value is going to be yk minus k minus 1. Yeah, that should be it. So f derivative So in order to test that, let me just get rid of this part here. Let's call x sine 2 times pi times, I don't know, 20 times t. Since we have a time vector, that shouldn't be a problem. And let's actually use this here. Plot t comma x line with 2. There we go. Now what I also want to plot is I also want to plot the derivative here. So x derivative is going to be f derivative, and then we use x comma t, and the derivative, let's have it red. So now integers or logical values, what is t? I guess because of let us basically redefine this. I'm not sure why it is an issue here. Let's see. Yeah, we have y. Oh, here we have k minus 1, and we are trying to use k minus 1 here. That was what I was talking about, so we need to use a better index here. So it did the job. Let's see. Yeah. First of all, I'm not sure about our sine wave. Let's drop down the frequency. Maybe that's the issue here, because our sampling time is not quite good. Therefore, yeah, let's increase the sampling time for now to have a smoother one. And there we go. Now, I'm not sure if it's visible, if there's an issue here, but yeah, it is. The red one is the derivative again, and as it was the case in the step response, you can see it drops down to 0. And again, the reasoning is the same when we use length t minus 1 is assigned, but the last one is not assigned. What we do at these times is, for the derivative most of the time, is we assign just the last value, k, to the previous value, because the sampling time should be small enough, and we're just copying basically the last value here, so it seems more continuous, but it's actually not that. But yeah, we just trick ourselves in order to believe that it is basically just the last value repeating, and it is smooth. Because the reason here is that if you have n points, then you will have n minus 1 differences. And what we're basically doing is we're just getting the difference here. There will be 1 point missing. It will not be the same length. Therefore, we're just adding just the last value. We repeat the last value or the first value. It depends on upon you. You can also repeat the first value and shift everything in order to get the derivative. Now, this is the conventional method here, but this is basically a more like a C approach. You can leave it as it is and use it in C. But I'm going to show you a much quicker and easier way. Since we're using MATLAB, I'm going to delete everything here, even this one here, and call it something like this. Let's call it a vector, and I'm going to use diff y. So this is basically the same. So let me show you temp. Let's have 1, 3, and maybe 10. And what diff does is the following. 3 minus 1 is 2, 10 minus 3 is 7, so it takes the differences between this. As you can see, we have 3 points, but only 2 differences. What I'm going to do is I'm going to repeat 7, so it would be 2, 7, 7, so it looks like it is a continuous signal. Or what I can do, I can repeat 2 here, so 2, 2, 7 could be used in order to generate a um, a same size signal here. And you might argue, well, it's not correct. Why can we do that? Well, the assumption in zero overhold method was that the tau value here, the time difference, should be going to zero. That's basically the assumption here. We should probably look at 0.1 seconds of time difference in the worst case scenario. In the best case scenario, it would be looking like this, 1 millisecond, for example. And in 1 millisecond, we can assume just one sample. We can repeat just one sample because we have thousands of samples, and just one sample would not bother us that much. So that's the reason why we can apply this. Now, dy here is going to be vec, but then the last element of vec. And by the way, I need to divide by tau because this is the difference divided by tau. So this is basically it. Let me repeat run one here. And you can see nothing changed. So let me close it maybe and open it. You can see I picked this because one of them is cosine, one of them is sine. So it should be basically it. Because of the time difference, you can see the gain is different. But yeah, this is basically f derivative. Now this was task 2 here. What about using the integral? Let's also create something similar here, but call it f integral. So let's call it f integral yt. Yeah, let's call it something else. It's not dy. I'm going to call it q. F integral. And we need the sampling time. We can also delete it. So how are we going to calculate the sampling time here? Since I've used a different notation, let's update our notation and our assumptions here. dq divided by dt should be equal to y. Now, if I use delta q, so qk minus qk minus 1 divided by the whole thing divided by tau is going to be equal to y here. What I can do is I can basically see that tau times y should be this, and qk should be this. So this is basically a summation. It should look familiar because the new value is the last value plus some sampling time times the signal itself. So yeah, and we need a for loop again. So let me just copy the for loop from here. We don't have for loop here. So from here, put an end, shift this here, get rid of this. So what we're going to do is we are going to need a signal called Q, which should be a zeros vector of size t or y. And what we're doing is we're using k2 to length t. The new value is calculated out of the last value, tau. I can just replace tau because tau is only used here. So t2 minus t1, which was basically the definition here. So you can see this is basically delta t times y. That is summed up over k equals 2 to the length t here. Yeah, this should be basically it because we're just adding stuff, and this is numerical integration. In order to see that, what we can do probably is just repeat this here, x di maybe, the derivative integral di, let's call it magenta, and f integral. So let's see what's going to be the result. Maybe length t minus 1 again, because k minus 1, no. There's no issue there. Oh, it's going to be yk minus 1 because not the whole vector, but the time instance k minus 1. It should be the same as qk minus 1. So let's run again. Let's see. Yeah, we have calculated the integral here. Now, there's a difference in terms of magnitude, but other than that, we should be okay. So if we look at the max value of xdi, I guess, and if we normalize that and then plot it, xdi, we should get rid of oh, that was not my intention. So divided by max di. There we go. You can kind of see that it is a shifted sine wave. Of course, we're not going to get the same. There are many reasons for that. First of all, the sampling time itself is a problem. But the thing that I'm trying to show here is that you take the derivative of sine, you get a cosine, and then you take the integral of cosine, you're kind of getting the sine wave here. So that's what I'm trying to get at. Yeah, let me see. Well, we are taking the integral of something else. So now it's even matching. Yeah, okay, my bad. I assumed that I was feeding it the derivative, but you can see I have matched the exact same signal here. If I drop down this maximum part here, if I don't normalize it, it still should mess up the scale, maybe. It didn't affect that much. Okay, nice. So we can see that we used a sine wave, we took the derivative, and then we took the integral, and it matches. So it's not that big of a deal. But again, if I increase the sampling time here, we kind of should see the effects slowly. But since the original signal is also crappy, it's not really that big of a deal. Let's increase it a bit more. Yeah, it even messes up the whole signal, but you can see the derivative integral, they just compensate each other and it's quite the same as it should be. So we can assume that our derivative and integral functions work. So let's move on. The next step is to write a simulation code that computes the step response of the closed loop of a p-type controller and GS based on the zero-order hold methods. So now what we're trying to do is we're trying to use a closed loop. Now we will use a controller KP and then the transfer function itself, and we will have a unit feedback so that we can kind of transition into trying to come up with a controller or trying to tune a controller, for example. So, yeah. Um, okay, now, uh, let me just basically copy run 1 here, call it run 2, and let's try to implement that part. So let me get rid of this. There we go. Now, before we look into the figure, the output, let me clear everything. So, first of all, our connection is not going to be the same. I can still use this and still use these, but the names might change. And the reason for that is the following. We will have a reference, and then a summation point, and then the controller gain, and then the transfer function, and this is going to be our output. And then this part here is going to be the feedback loop here. Now we know that we call the signal E and we call the signal U. So first of all, the first thing that I'm going to change is this ones here. It should be zeros. But what I can change is this is going to be the reference. So this is the reference here. And I need the output here. And then we have the error signal here. And then the control signal here. So this is kind of the, these are the signals. And X is going to be something internal, as it is. Now, we have already implemented the portion here, this portion here, when we use U as a vector of ones and Y is the output. That is called the open loop, and we've already done that. Now our simulation will begin with the following. We have some additional equations here. For example, one of our equations is the error that is defined as R minus Y. And then we also have something else, which is U equals Kp times E, because Kp is here and U is Kp times E. And that is actually all that we need to do here. And remember that our time instance now is K minus 1. So when we're working at the time instance now, we're meaning K minus 1. And the future value is K. But the future value is only important when you use the dynamic equation, which is line 41. Other than that, you don't really need that. So when I have these two equations, since these are not dynamic, and you might guess the reason why we start with the p-type controller and then transition into the PID type controller, because the p-type controller has only static equations, so we don't really care about anything else. It's going to be quite easy to implement it because we only have these static equations. But if we are looking at the PID type, which we are going to do in a moment, then it will be different. But the easier version here is the p-type controller, and you can see why. We don't need to use the zero order hold method or anything else because that's already done here, and we need to just change basically the or add the necessary extra equations for this connection here, and we're going to be good to go. Now these are static equations as it was the case for y equals cx. So what I can do is I can just add basically k minus 1 to all of them. Rk minus 1, Yk minus 1, Uk minus 1, and E. Of course, we need a Kp value. So let me just generate one. Maybe Kp equals 1. I don't know. Maybe a lower value. We'll see. And yeah, that's basically it. Now, we need to know what the error is. We need to know what the control signal is. Based on these, we will apply this to the system. The system will generate an output, and that's going to be it. Of course, I have moved two static equations. So what I'm going to do is I'm going to also have them down here with k, the last value here. This is because of the missing term here, the last term. You might just start from 1 here, or length t minus plus 1, and then use an if statement and then do something about it, but I like to just append these static equations for the last time instance. Now, this actually should be it. The order here is important because we apply R from here, and then even though the system didn't react, it has some initial values, and since we're dealing with a transfer function, it is probably 0. So the output will be 0, and R minus 0 is going to be the whole error here. It would be E equals R, and Kp times R will be the initial input that we are going to apply to the system. but the system has one sample to react to it because we are using zero overhold method. We assume that during the time differences, everything is stable, even though in continuous time that's not possible. So, but we keep it a glimpse of time, so therefore that's not that big of a deal. So we then end up in the next sample, and then the next sample again starts from here. Our k equals 1, or r1 minus y1, e1, then u1, and then y2, and then r2 minus y2, etc., etc. So this is the way we are basically imagining stuff happens in terms of time. So before I transition into testing, what I can now do is I can come up with a subplot here, or even a combined plot. It depends. Let's have a combined plot. Let's plot everything here. So we have R, which should be black, and which we call reference. Let me, by the way, append a legend, and then show, and then location best. You can use this location best because it will just position itself. So error should be, I don't know, let's have a color for that. You can just give RGB values, so 0.4, 0.4, 0.4, and then we have the Y value. I'm not going to plot X's, so why not? Let's have a blue one. We can also see the control signal here, which which is going to be a different color. And let's see. Oh, we're still running run 1. I'm sorry. It should be run 2. There we go. And we have an error. And the reason behind that is that I forgot to say display name. So this is basically output, or let's call it YT. This is going to be UT. This is ET. Let's call this RT. Yeah. Now we need to apply a reference. So it should be ones, not zeros. There we go. Of course, I need to increase the KP value here a little bit. Hope that I don't mess it up. Let's see. Did we forget something here? E, U, maybe the ordering. Yeah, the ordering is, oh, but yeah, the output doesn't really depend on that, but yeah, it fixed it. Now we have the reference, which is 1. We have the output, which is Y. The error signal is on top of the on top of that. That's a bit interesting. Yeah. Oh yeah. Oh yeah. Okay. 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 I forgot. As you can see, the ordering matters. Now when I change it, you can see the whole simulation changes, basically. We can see it. And let me explain why. Because here in line 41, R is already set, but we didn't calculate Y. And this one sample difference, when we calculate one sample later, it loses its meaning. So why k minus 1 wasn't assigned, you should always start with the output of the system y here, because we're measuring it. And we take this measurement and take the difference and then apply it to the system. If you mess up the ordering, you can see the simulation does not help out. Now we can see we have a steady state error. That's because we're using a p-type controller. If we increase it and if it's not unstable, if it's still in the stability range, yeah, we can see it's not that ideal. Let's change it to 50 maybe. Then we get this effect here. Of course, the brightness of the control signal is not nice. So maybe it's too bright. Let's have maybe 6. So it's RGB, so I'm just coming up intuitively with some colors. Yeah, that's better. But you can see since the scaling is off, we have an interesting thing going on here. But you can see the power of MATLAB and the power of this simple piece of code here, because we have basically eliminated Simulink. Even though in the last lesson we've talked about Simulink, it's not really that necessary. I recommend you Simulink when you have complex, very complex systems with subsystems, etc., because then the code management here will mess up. But if you're interested in just one feedback loop, then I would suggest you to use this. Maybe not zero overhold method, of course. You might opt for Runge-Kutta 4. And the reason for that would be, of course, faster calculation times. Yeah, we will talk about this at the end of today's lesson. So you can see the error, the step signal here. The error drops down throughout time. The output rises, but we apply some heavy input here. We can see that the input is basically 50 here. It seems like for quite some time the system does not respond here for some reason. Maybe there's a slow, I don't know, some pulls are slow, seems like it. PZ map GS, well, not really. We have one which takes 4 seconds to settle down, and we have some faster pulls here, but yeah, it is what it is. Now, of course, this topic is not really that much interesting, because we only have a p-type controller and it's not that wide of an application that we are going to be interested in. So therefore, let's transition into the PID portion here, and let's talk about PID. So I'm going to start with basically the same. Let's increase this to 100 here, and then KI maybe 10, I don't know, KD maybe 10. I'm just coming up with values here. And I'm not going to change anything about this. But now we have this PID transfer function here. So FS. And that's also that's going to be the only difference that we will see here. Now, again, everything stays the same, but yeah, we need 2 additional signals. The reason for that is we need a linear combination of the following. So it's going to be Kp times E plus Ki times, I'm going to call it Q, and then Kd times S. Well, originally these are going to be the following: dE divided by dt, and then E times dt. Um, it is going to be Kp times E, Ki times dE dt, and Kd times e times dt, of course, the integral here. So, I've basically chosen the names here, q, because we already used q here in integral here. So dq dt, or q is going to be e dt. So we're going to choose that as q. And the reason why I've called it s, it seems like it resembles me the integral signal here. Oh, by the way, the derivative should be here. This is going to be e dt. This is going to be dE divided by dt. So I'm just rolling with q and then s, and we are going to calculate them. And we're just going to take the linear combination. If you know the meaning of q and s, you can just see that the controller just is a linear combination of those three signals. So it means that our control signal here, which is going to be this one here, is going to change a little. And in fact, it's going to add some two additional terms. And I'm going to add ki times q and kd times st. So I've updated my control signal now. So this portion here is updated. But we need to generate the required signals from E here. So let's also call them q and s. And other than that, we should be okay. Now, we have our, oh, this should be CD all along, by the way. I've seen it now, so let me just change it. Since the CD is equal to C, it didn't matter that much, but we're using AD and B. Oh, we didn't even use. Yeah, of course. Well, you get the idea. This should be BD. We should be more careful about our codes. Let me just quickly fix it here. BD, and this should be CD. That makes more sense. So, since if I change anything here, then I would mess up the whole code. We should be careful about that. CD, keep BD. Yeah, seems to be all right. Now, and BD. You might probably use TF to SS, so that therefore it's really important. Now we have our output. Then we have our error. At this exact point, we need to calculate two more signals so that we can take the linear combination here. And we know from F integral that this is going to be the case here. So I'm just directly taking it here. So qk minus 1, I know what the sampling time is, tau, but I'm not taking the integral of the output or any other vector, I'm taking the integral of the E signal here, the error. So that's that. That's also nice. You can stop here and drop KD in order to use to calculate a PI controller, because KD is not implemented yet. But if you keep KD 0, this would be the PI code here. Of course, this is the dynamic part, so that's not necessary to add. Yeah, this is essentially PI. Now, but let's add the derivative part here. So I'm also going to take this. Oh, by the way, I've changed it, so I cannot take it. So let's do it here on the fly. It's basically the difference between k minus 1 and k minus 1 divided by tau. That's basically what it is. This is going to be S something here. So, well, since the time instant now is k minus 1, I'm going to use k minus 1. And you can see k minus 1 is used here. But the problem is that we don't really know what the value of k, ek is. So basically this should also be ek minus 1. But then I'm using ak minus 1 minus 1, which doesn't make sense. So I'm just going to shift the differences by 1. And by that, I mean the following. We can use k and k minus 1. There's also a formula where you have k plus 1 and k. But it's really not that important if you have a small enough tau value here. Therefore, we are trying to basically use that fact. Now, and since I don't have ek, but I need ek minus 1, I am kind of adding a z to the power of minus 1 if you use Simulink. It's just a delay, basically one sample delay, to the derivative itself. Because when we talk about PID controllers, we always talk about the fact that they are not quite realizable. And the reason for that is we need prediction. But the way that we overcome prediction is basically we're looking at the previous differences instead of looking forward. We're kind of looking a little bit backwards instead of predicting the future, if that makes sense. And this is also the equivalent of a sort of derivative. What you can, by the way, also do is you can just come up with a system that looks like s plus, yeah, something like that, s plus maybe 100. We can add a pole far away to the derivative to have this kind of derivative effect. And if you use the PID from Simulink, or if you use Simulink, there's this coefficient n. This corresponds to that coefficient n, which is the filter coefficient of the derivative term. But yeah, by the way, you have to also provide 100 here so that you don't mess up the gain here. Or what we like to do most of the time is just use it like this. So s divided by 100, or 1e to the power of minus 2 times s plus 1. So that's the reason why the n value is going to be 100, because it's 1 divided by n, something like that. You can just check the PID block from Simulink. So here we would have then a first order system. We would convert that, but then keep in mind we have this by proper thing here, because we've talked about this. I have used basically this PDF here, and here you need to again start from scratch from here in order to convert the derivative transfer function into a system here. So I'm just showing you the most used version. What you can do is you can just pick individual transfer functions and replace them with difference equations. But then you have to have a naming scheme in order to not mess up everything. So yeah, everything is possible using the code portion here that I'm showing today. But what I'm going to do, instead of bothering with all that stuff, the easiest way as an engineer is to just go one back and just assume that if k is greater than 2, because I'm not going to be able to calculate this if k is equal to 2, because 2 minus 2 is 0, and 0 index is basically not available in MATLAB. I could also increase this one here, but I don't really want to. What I'm basically doing here is I'm waiting one sample for the derivative to take action. You might argue that this might be problematic, but I would say that the tau value here will be 1 millisecond or 10 millisecond or 100 millisecond at most. So 100 milliseconds of difference or waiting is not important if your settling time is 5 seconds, 10 seconds, even 1 second. It doesn't really matter that much if you look at it that way, because we have thousands of samples, and just one sample is not really that big of a deal. And the core assumption here for accuracy is that tau is small anyway. So if tau is small, then this weighting is even smaller. So yeah, that's the reason why we can use this. If you have used Simulink and if you have encountered an algebraic loop, this is exactly what it was. If we use ek and then minus ek minus 1, this ends up being an algebraic loop. And if you add just a z to the power of minus 1 or just one sample delay, then you can solve most of the algebraic loops. But you should be careful, because you should know what you're doing. Otherwise, you're just adding everywhere z to the power of minus 1 and then expect the system to work. That might cause some issues too. Now, yeah, well, let's see. We start off with a PI controller for one sample. And the first sample is also not really important because that's the initial step. So 2 samples of waiting in order to get the derivative going. But that's exactly the shift, and looking back to the history of the system instead of looking for prediction is the portion that is going to be like a derivative. So it's a delayed derivative, sort of. Yeah. Um, let's see. Let me check twice here. Yeah, that should be it. Now then we add this to our system, and from these here, do I need to update anything? Maybe, um, I guess this one here, because this is also static. So after E, we would have S, K minus 1. So K is going to be that, so this should be minus 1 divided by tau. And of course, we have this one here, which is not correct at the moment. Let me fix that. So K. So there we go. These are not really that necessary. What you can do is you can just plot one sample less. So you could do 1 up to n minus 1, and you don't really need to do this. But when you do that, instead of seeing 5 seconds, you might see 4.99, something like that. So I don't really like that, so therefore I'm just generating this. But you can just skip this if you don't want to bother with that, and just, yeah. Or you can just increase this by 1 sample, and then again plot the 5 seconds part. There are numerous solutions to this, so go with the one that you like the most. So, yeah, what I can do now, which is even more interesting, is I can look at the different signals. But I guess I should now separate them. Yeah, well, let's don't. Let's just go with it. So this is basically integral EDT. This is d EDT divided by dt. Control signal. Let's have that. Hope that the coloring is good enough. Let's see. So this is going to be round 3. And yeah, let's pick a lower KP value here in order to see what's really going on here. So I'm not quite sure if I have a good coloring scheme here. This signal seems to be the control signal. Here we have, yeah, stuff going on. Yeah. Okay, let me just change 2 colors here. Let's have red, full red. I'll just drop that. Let's have red. Let's have green so it strikes, so we can separate them much better. Blue, and then the output should be, I don't know, maybe magenta. And we have black, and then we have this weird color, which is not really that important at all. Yeah. Now, we can zoom in here and we can see the different actions. So this is the error signal here. So error starts out as 0, drops down to a certain value, and it keeps dropping down. And we have the derivative part, which starts from 0, but then increases like this. Oh, that's, by the way, the integral. I'm just messing up stuff. I'm sorry for that. And this is the integral portion, I guess. Yep. So then we kind of have this magenta output, which needs some time to reach the value 1. And we have this control signal here. Now, of course, the aim of this is not really the PID controller or the optimality of it, because that's going to be the next step here. But you can see that I have different information about the error here. We have the derivative, kind of. We have the integral. We have the error itself. We're combining them linearly with some coefficients, which we call PID coefficients, and then we end up in a control signal. Then I can use the difference equations and the zero overhold method in order to simulate this. And the dependency on MATLAB is almost zero here. Because I was lazy to code this part, you can just do that and get rid of everything. So yeah, the only thing that would be left would be the setting time here. You might also have some algorithm for that. Then you can port this whole thing here into any programming language that you want. And by any, I most of the time aim to mean C, because there are some libraries. For example, if you want to use CUDA, you just provide C. You can port this to CUDA, use an NVIDIA GPU to try to do it like 1,000 simulations at once. That's what we can go from here. So, and the next task is about the genetic algorithm or the FMINCON functions that are available in MATLAB. Let's use this in order to optimize the the PID controller that we have at hand. So let's try to do that. Now for this, what I need to do is I need a little bit of structure, code structuring here. And the reason for that is basically we need a main function that will have some setup, and we will then also have a function that will calculate basically the quality of response, sort of, or the objective of our optimization. So this will be basically the portion that will be available in that. So let me just open up a main GA maybe. So we are going to use the genetic algorithm here. Now, you can, by the way, use help GA and read the documentation here, or even doc GA here. I will just dump the whole thing on the screen and show you how it's working and what you can do with it. But you can, for fine tuning, for more options, you can just check what we need here. But the basic things are the following. We need a fitness function, which is basically the objective here. We need the number of variables. A inequality, B inequality is basically AX, so AX, A times X less than less than or equal to B. So this is basically inequality. So what we're trying to do is the following: minimize X such that the following restrictions hold and X is minimum. X, by the way, is our decision variable, and the length of X is basically n vars here. So that's what it is. The number of variables is basically the length of X. So you can see that X is a vector. Now then we have equality constraints. So A equality X should be equal to B equality. So that's another thing here. Then we have lower bounds and upper bounds. So lower bounds less than or equal to X. Also X should be less than or equal to upper bound. So when you want to put some boundaries on your decision variables, non-LCON is the nonlinear constraints that is going to be the function that we need here. So needs to be implemented. This is the most tricky one here, but this will use our simulation, zero overhold plus PID simulation that we've coded so far. So this is going to be a nonlinear constraint. There is some integer variable stuff on the options and RNG states that we are not really going to be interested in. And we have X and fval, fval being the fitness function value, the best that it could came up with. And we will have this this GA, and we will use this notation here. So that's going to be basically it. We have some population output stuff. I will show some stuff about that. But in a nutshell, this is basically any minimization, optimization kind of templates that we can use in MATLAB. We will use this for FMINCON and genetic algorithm. They have their differences, the way of solving, but we're not really interested in that at the moment. You should study those lectures on their own. But this is just going to be an example, and you use GA or FMINCON on your own anyway, so why not show it in here? So, first of all, in our main function, we will call something called RNG default. And this will set the random number generator to a certain value so that we can F5 it and get always the same result. The repeatability of the result is important because we want to debug it. Once we're done with it, we will disable it and just go with it. So we're fixing this for if we run it again and again, we will end up in the same results. So it's not random now. We're fixing it to a certain value, but it will be. Now we have our transfer function. So this portion here, the transfer function, the numerator, denominator, and basically up to here somewhere, we should be in the main file. So let me just pick this whole thing here, dump it in here. So there we go. Now this is the conversion step. I'm just going to have that. We need a time vector, which is important. But other than that, let me remove this here. There we go. So the only problem here is this t here, nothing else. Yeah, that's basically it. So, what is our x vector? Well, our x vector is going to be the following. Let's call it kp, ki, and kd. So that's going to be our x variable here. Now, therefore, let me generate the lower bound for them. Maybe I want to work with only 0 values here, so zeros and 1 by 3. Let's put in an upper bound. Let's have 500 so that we don't end up in very big numbers. 1 to 3, 1,3. So yeah. Now we're going to use GA and then a certain objective function, which I don't have now. We have used this notation in the last lesson or video too. You can check it out. This is basically the way of a function pointer that is used in MATLAB or a lambda function. Yeah, that's basically it. So for a number of variables, we might also define it. And vars is going to be the length of LB, the lower bound, and vars. Now, from here, so we have provided n vars. We don't have inequalities. We don't have equalities. So A inequality, B inequality, A equality, B equality, they are basically objects that are just empty. And then we will have lower bound and upper bound. What we still need is the nonlinear constraints. Oh, I was wrong about this. Nonlinear constraints, we don't have them. It might be, for some reason, you might have something like kd squared times kp should be less than 3. Then, for some reason, I don't know what the reason might be, then this is the nonlinear constraint because it's not linear, so you should define a function that does this using the x vector here. In our case, this would be x3 squared times x1, something like that. So it should return this as a function, but we don't really need that, as I've already mentioned. So, yeah, we will also have some options. But let's first skip those options. Yeah, the easiest way we can get something out of it. It is X, fval, E flag. Those are all given here. So exit flag, etc. We can also define something like output, population, and scores. Maybe it would be important, maybe not. We'll see. Yeah. Then we will have just X and nothing else. And we'll talk about that later. So that's basically our main function. So it takes the system, converts it into some data that will be necessary in our objective function, and we've just set up some lower upper bounds, number of variables, stuff that is necessary for the genetic algorithm to run. So now we need the objective.m function here. So let's call it obj.m. It's the function obj, and it will certainly return something. The value, it will take some x, and there we go. Now, first of all, let's extract the values from x. So kp is going to be x1. I set it up like this. You might change it, but I assume that this will be ordered. So kp, ki, and kd values will be populated. The first one is kp, the last one is kd. This is kind of the protocol that I have set up myself here. There's no indication that this is the case, but I assume it like that, and that will stay. If I have x, I will take the first one as kp. So what I'm going to do is I'm just going to take this, place it here, and use them like that. So this is the protocol that I've defined for myself. So once I have that, you can see we will look for step responses. We need this whole thing here. So let's dump it right in here. Now, yeah, then we will calculate that. So what are we going to optimize? So there are many things that we could optimize. The maximum value of y, maybe the settling time. We need to first write a function that calculates the settling time using this for loop here maybe. But I'm going to keep it simple. You can just customize it as you wish. So what I'm going to do is, since we have a E signal here, the error signal here, I'm going to try to look for the, which one was the E signal here? So the red one here. So what I'm going to do is I'm going to take the integral square error of this signal and try to minimize it. This is just a basic optimization. I don't really care about the optimization itself. I'm just trying to show you how you can use this code, how you can use genetic algorithm and combine them. You can also, by the way, combine this objective function with Simulink last video, because there we had some code that opens the Simulink, runs the Simulink file, gets some values out of it, and closes it. So you can basically plug it in here into objective.m in this file. Instead of this, you would have something like mdl equals the model name, model.slx, or the name itself, and then some sim mdl, and then you have basically sim out or something like that. Then you can just transition into your objective value. So you can also use Simulink here instead of this, but I'm just showing you the pure code version here. So it's quite powerful to use Simulink and genetic algorithm or FMINCON in cooperation with them. So yeah. Now let's take the sum over this here. Well, I use sometimes some notations, but let me show it to you. If you have 1, 2, 3, if you use a dot to the power 2, it's going to be element-wise squared. And if you take the sum of it, the sum function just takes the sum of the whole vector. You can use it, and if you use square root, you will have that. You can also divide it by length, but everything is same sized, so I'm not going to divide it. It can stay like that. Yeah. Now you might ask yourself, isn't there a problem? Um, there should be a problem because, first of all, the function doesn't take t. It doesn't know what CD, AD, and BD are. Yeah, and it doesn't know what tau is. So, yeah. But we might skip the tau part because we can calculate it. How can we use basically these here? The problem is the following. I can maybe wrap it in another function as I did it in the previous lecture for the OD45 function, but I don't really like that idea at this point because it's going to be too complicated. What we can do is we can do the following. Remember that, for example, this script has a memory on the workspace, but the function itself has its own local memory. This goes for MATLAB, for C, and other languages. A function is written because you want to have a local space to reuse the variable names, etc., and you don't really care about the global memory. But in MATLAB, what you can do is you can declare variables global, and if you do that, you will be accessing them inside of a local variable or a function. So local memory or function. So what we are going to do is, from the beginning of our script, um, let's say here, after these maybe, we will define that, for example, the time vector will be global. So global t, global ad, global bd, and global cd maybe. I guess these should be enough. So I'm going to copy this too, and this part is important, also here. So you are basically telling the memory or MATLAB that these names are from the global workspace, from the global memory. These are not local variables. Therefore, I don't really have to assign them here because they're already assigned, I assume. And yeah, that's basically it. So this calculation then can also be done in here once we've done that. And I have acquired t, so I should get tau. I have AD, BD, CD. I guess we should be okay. So before I run this, let me do something like this. What I can do is I can just call my objective function to see if it's working or not. Using, for example, 50, 10, 10, which was the previous example, I guess. Let's try to run it. Main GA. There we go. It gives us 2.72. This was basically the example here, which we've run in run 3. You can see these are the KD value. 50. Oh, it was 50. Yeah, it is the same. And we just have run basically the we didn't run the optimization. We just showed that if you use 50, 10, 10, the square root of the error or the ISA value of the error is 2.72. So yeah, if I, for example, decrease this, let's see what happens. You can see it's even more. So the genetic algorithm somehow should come up with better and better PID values over time. So let's open this part up. Let's open this up and let's try to run it. So it displayed a message and it came up with PID parameters that are the following. Of course, the interesting part now is that we don't really know what we should do with it, or we don't really know if it's a good one or if it's a bad one. We can check for FVal, and yeah, we get 2.18, which is a better estimate than which I came up with. But yeah, we want to visualize stuff here, so yeah. By the way, let's check what E flag is. And as far as I remember, if E flag is equal to 1, If E flag is equal to 1, then you succeeded to optimize it, or the optimization terminated uh, with a value, basically. So let's have the PID values here. I'm not going to again use my zero overhold methods to not overcomplicate it here. But basically, I'm just going to use the control system toolbox because I can. So I'm just going to do that. But what you can do is you can maybe separate the simulation from the objective function here. Because we have everything available here, what we can do is we can have another function and call that function inside of this function, and it will just return the objective value, whereas when I call it externally, the function that will get rid of this part here, I can just simulate it with the same code. That's also possible, but this video is long on its own, and it's complicated. I'm not going to bother with that. So I know what KD is, KP is, and KI is. Just plug it in. I know what the transfer function is. Just use feedback. But in terms of portability, we shouldn't really use control system toolbox. But yeah, that's on you. If you're porting it, then you should basically take care of this. So what we can do is we can display some messages. Let's have a nice output here. The controller looks like the following. We have KP plus string KP KI KD, and then we can also have some overshoot. We didn't really look for overshoot, but you get the idea. We can do that actually. Settling time. We're not looking for the fastest, but we could. Let's open up a figure. Maybe a subplot. And then Y. I'm just going to save the handle here. And then we have another subplot. There we go. Maybe we're going to display the poles and zeros. Real, imaginary. Pole zero map. Then y comma t is equal to step ts, and then plot onto x1 t comma y, line width 2, and then get the poles and zeros. Real zeros, imaginary zeros. So these are basically stuff that we could care about. I'm just and then that maybe poles go. Otherwise, we're done with it. So yeah. Well, we should have some separation here. There we go. There we go. We see that overshoot is 0. 3.41 is basically the response. And then we see there are some poles and zeros there. And we get this result here. Now, we can also do some fancy stuff with the genetic algorithm. I'm going to just use these options here. Remember, we had some options. So optim options is going to be the thing. So for GA, what we can do is we can provide a plot function here, and the plot functions are basically going to be at GA plot best fit, basically GA plot genealogy, and also maybe the scores. So some GA related data, basically. GA plot distance. These are all in the documentation, by the way. I just picked them. Plot selection. And then you can also display the iterations here, because it didn't really display that much. So when we provide the options to that, there we go. We can see that. By the way, we can also use some timing on our optimization. We have this tick and tock thing here, which is emulating the clock sound. So if you call tick and have a semicolon and then tock, the value is going to be displayed automatically on the screen. When we run it, there are some visuals that didn't appear immediately, but you can see stuff happens here. You can see the best fit, you can see the generation, the function count, the best it got. It's optimizing. Of course, since it's also plotting, it slowed down the optimization. We can see it kind of hits a boundary here. It terminated. So we can see how many generations, function counts there are. And I'm not sure, but we can basically get that stuff also to document. Hopefully it will stop now. It didn't stop. Yep. There we go. We get basically 77.5 seconds of elapsed time. Why did it plot on top of that? I don't know. Maybe we should call figure 1 somewhere here. I don't know. Maybe somewhere here. So figure 1, so it plots on figure 1 and does the other job. So what is displayed in output? You can see it gives us some information. We used some generations, 128 generations. 6,000 times is the function count here, which means that we are using this objective.m function. We're calling it 6,000 times. So that's what I mean by using a different version here. if tau is problematic, or if you want to have faster code, because our sampling time is not quite there. You can see we are using 0.1, but we're okay with it. If I change this to 0.01, you can experiment with that. You will see it will slow down even more, even further. And that's not a nice thing that we want to have here. We want to have the fastest simulation code that is possible and the most accurate one. So the Runge-Kutta, fourth order Runge-Kutta algorithm here would fit our needs the best, in my opinion, because we could then have here some multiple calculations, but it would drop down the amount of 4 cycles here, 4 loop cycles, and that would then end up when better accuracy for higher sampling time values here. So this is basically the genetic algorithm version here. By the way, I can also comment on the results here. We can see that there are some almost pole zero cancellations. The optimization hit a boundary here. It tried to get rid of 2 of the poles with the zeros of the controller, and it is then left with basically a pole pair, which we call the dominant pole assignment here. And it's going to be the topic of control system design lecture. But yeah, you can also sometimes, if you have the theoretical knowledge, see why this can be optimal, because they will cancel each other out and you will have 2 poles. It will get some overshoot and settling time values. Yeah, this is basically the solution for the genetic algorithm here. So let's also look at the FMINCON version here. So let me just copy this and practically paste it here. Call it main FMINCON. So now we don't read any RNG here. So we have our transfer function, again the same stuff. And here we have some initial point. So clear CLC help FMINCON. We can look also for, it has kind of the same structure. You can see it is, again, an optimization tool. We can have a objective function here. It has some algorithms, interior point, SQP, trust region, active set, etc. It uses a bit different stuff here. This looks more familiar with us. We have x0, so I'm going to call it x0. X0 here, drop the upper bound, or maybe leave it, I don't know. So let's copy it, call it x0. So then we have lower bound, upper bound. We don't have number of variables as far as I remember. So get rid of that. So options now, this is going to be FMINCON instead of GA. Here we provide the function, FMINCON function pointer, sort of. As far as I know, we don't have this plot function thing here. So let me get rid of that. We can choose the algorithm. Let's choose interior point method. And we can have some max iterations. You should just read the documentation because it is tool specific. So yeah, therefore. Let's also have some max function calls, function evaluations. 1e6, so 1 million is kind of the boundary that I'm setting. And we can again display the iteration here. These are not necessary, these are not really obligatory, but I'm just adding them to showcase it, basically. Display, sure, that should be it, basically. Now, since we don't have that, I can just get rid of this. We have X, fval, E flag, and then output and lambda, seems like. It should be down here somewhere. There we go. I'm basically using this one here. Then we have timing, and then again, E flag should be the same. I'll put the same result. So I didn't basically change the objective function here because the objective function is between x, some decision variables, and the value. Everything between these two definitions is basically covered with this global stuff here that is necessary to calculate stuff, and it doesn't really depend on anything else. So if we have those, we're good to go. So we can use the same objective function if we code it more universal with the main GA with a genetic algorithm, or we can change the solver here, and we can then run that one here. So main f MINCON. We have messed up stuff here, so let's see. Oh, we didn't, yeah, my bad. So let me just change this one to FMINCON, and then we have the objective. We have x0, it takes an initial point, and then lower bound, upper bound, and options, seems like it. We have another problem, line 35. Probably we did mess up. Yeah, there's an extra comma here. There we go. So yeah, it took less time, it used less iterations, and it directly hit the target here. And we kind of get the same result, as you can see. The reason is that I've picked a system that is specific, so I can show you that the optimal is kind of the same, but the way and the amount of time that you need and computations, that may change. Not always is the genetic algorithm the way to go for your problem, for your solving, because it might not be suitable for your problem. Of course, our course is not really that much about optimization itself. It's a whole topic on its own, but knowing to try the tools out as a student is quite important. And at this stage, you should be able to just run them maybe, and then get the idea behind the FMINCON, what it is doing, what maybe GA is doing. By the way, there's also lots of other functions. So help, FMINCON, it's not only minimization. You have actually fmin search and stuff like that. So if you look at the documentation, you can just go with that. You can also use for Optim tools. It's a tool on its own, so I'm not really covering that part. So you can just check it out on your own. But what we've done today is we've just used the zero order hold methods in order to solve a differential equation that represents a transfer function. And we've used basically the idea of taking a numerical integral and derivative in order to implement our PID controller. We have embedded our PID controller into the differential equation solving methods. Here an objective function, object obj.m, and you can see we have a nice little function that gets rid of all the necessary stuff. And as I've already told you, you can just do this whole thing in C. You can just code it in C and use some CUDA tools, some GPU stuff, base stuff, so to increase speed even further. Yeah, it's quite interesting what you can do with this. You might also enable some parallel capabilities of GA or FMINCON if they have. As far as I know, GA has some parallel computations, but it's a bit more limited than what you can do when you take the whole control on your own, but still quite nice to use this stuff. Hope that this was helpful, so see you in the next videos.